13.1. In this video, we're going to go over multiple different topics from summation notation to functions, how they are labeled as far as f of g, h of g. We're going to be taking a look at graphs and various topics such as that. We're going to begin with our summation notation. And first, let's go over the actual look of our problem and how to be able to read that problem. So, generally within a summation notation problem, we're really looking at some form of sequence. Whether they're consecutive numbers, even numbers, odd numbers, it is some form of sequence within a start to stop number. Now, in the problem that we're seeing as an example below, we can see that it says the sum of k equals 1 to 5, with the equation being 2k. Now, in this case, what this means is that our start number is 1 and our stop number is 5, meaning we're going to hit every single integer between 1 to 5. So 1, 2, 3, 4, and 5. You can see that in this area over here to the right-hand side. Generally, that is written down so that you're able to find your answers while being able to identify which number it would go with. The next part would be after you've inserted and grabbed that first digit, which is 1, you're going to plug it into your equation. Now, in this case, we have 2k as our equation, so 2 times 1 would give you a value of 2. 2 times 2 would give you a value of 4. 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10. Once you have each individual answer for those given numbers, you're then going to add all of your answers together. So in this case, 2 plus 4 plus 6 plus 8 plus 10 will give you a final result of 30. We're going to go ahead and look at a couple sample problems of summation notation just to get a better idea. Let's take a look at number 1. For number 1, we're going to begin with first writing down all of our numbers that we're working with. Notice we're starting at 1 and we're going to 6. So we have 1, 2, 3, 4, 5, and 6. When focusing on these numbers, we have to take a look at the equation. Now, since our equation is just n, we would be inserting each individual numbers into that equation, which would result in that number remaining the same. So here, when we plug in 1, answer would be 1. When we plug in 2, answer would be 2, answer would be 3, 4, 5, 6, as we work our way down the line. This means that our total answer of our sum would be adding 1 plus 2 plus 3 plus 4 plus 5 plus 6. For this problem, notice 6 plus 5 is going to give you 11, plus 4 is 15, 18, 20. Our final answer here would be 21. Now, let's go ahead and take a look at example 2. In example 2, we have a very similar problem. We have the sum from k equals 3 to 7, with the equation being k squared. Now, for this problem, we're going to go ahead and write down each one of our numbers. So that would be 3, 4, 5, 6, and 7. We're going to go ahead and plug in each one of those numbers into our equation of k squared. So this would look like 3 squared, 4 squared, 5 squared, 6 squared, 7 squared. You're going to add the numbers at the very end, but before doing that, we're going to find the answer for each one of these. 3 squared would be 9, 16, 25, 36, and 49. Remember, we are doing a summation notation, which means we are adding all of these numbers against each other. Now, as we start working with these problems, we're going to go ahead and add each one of them, which will give us a total of 135. Let's take a look at example 3. In example 3, we are taking a look at the sum from 2 to 5, and our equation is 1 over 3 to the k power. So we're going to begin with writing down our equation and the numbers that would go into it, which would be 2, 3, 4, and 5. We'll go ahead, plug in our numbers into our equation. So this would give us 1 over 3 to the second power, 1 over 3 to the third, 1 over 3 to the fourth, 1 over 3 to the fifth. We're going to solve each one of these different problems, and this is going to give us 1 over 9, 1 over 27, 1 over 81, and 1 over 243. Because they are all multiples of 3, you know that they would work all with 9, which notice 9, 27, 81, 243. 243 would be our common denominator. We are going to need to add each one of these fractions together. So in order to do that, we first start off by finding a common denominator, which would be 243. And we're going to need to find a new numerator for each one of these fractions. We go ahead, we divide 243 by 243, which is going to give us 1. 1 times 1 is 1. 243 divided by 81 is 3. 3 times 1 is going to give us 3. 243 divided by 27 is 9. 9 times 1 is 9. And our final problem, 243 divided by 9 is 27. 27 times 1 is 27. We're then going to add our numerators, which would give us 40 over our common denominator, which is 243. If you have the ability to simplify, you go ahead and simplify, but in this case, 40 over 243 does not simplify further. Example 4. We go ahead, we write down the numbers we will be including within this problem, which would be from 1 to 6. So 1, 2, 3, 4, 5, 6. From there, because of the equation that we are working with, and it does involve a little bit more, we're going to go ahead and solve the first portion, which is grabbing each individual number and squaring it and placing it within that problem. So here, 1 squared would be 1 minus 10. 4 minus 10. That's coming from 2 squared. 3 squared would be 9 minus 10. 4 is 16 minus 10. 25 minus 10. And 36 minus 10. From that point, we're going to go ahead and solve the remaining part of each individual problem. 1 minus 10 is a negative 9, and we're going to add it to our next number. 4 minus 10 is negative 6. 9 minus 10 is negative 1. 16 minus 10 is 6. 25 minus 10 is 15. And 36 minus 10 is 26. You're going to add each one of these numbers together, and you're going to end up with a total of 31. Let's go ahead and take a look at slide 2. Slide 2 is just your homework. So keep in mind, just open up to the page. We're going to be looking from 29 to 38. Let's take a look at slide 3. For slide 3, we're going to be evaluating functions from a graph. The first thing to understand is the difference between dependent and independent. So, easiest way to kind of understand this would be Dependent is whenever something relies on something else. A great example, considering how it's April and taxes are going on, minors are dependent of their parents. So, considering how children are dependents in the eyes of the IRS, and it is tax season, what occurs is without something else, that function, or in this case, that individual item that we're talking about, would not be able to be resulted. So we're going to take a look at this equation. It says the total cost f of x depends on the number of CDs purchased, which is x. So our independent variable, which is x, is a standalone number. That number can just be there and it would be perfectly fine. Our f of x depends on the x value in order for it to have a value as well. That means that as the x, which is independent, changes, so would our f of x. This is the reason why f of x is considered to be dependent and the x to be independent, because as the independent x is there and you have a number for that, it will just stand alone. Your f of x would vary depending on the number of CDs purchased. When we're taking a look at a graph, you're going to have the independent on the x-axis and your dependent on the y-axis. Now, as we start going into function notation, keep in mind this is just understanding how we can go ahead and label each one of these functions. First function would be f of x. Second would be g of x. And the last one would be h of x. What this is talking about, this f, g, or h would be a label for the function. While the x is describing your x variable. Now, in the case that there is an actual number in there, it is basically saying that in the place of x, we will plug in whatever the given number is. So it may be 2, 5, 15, 432. The number one thing is understanding that if it's inside of those parentheses, it is going to take the place of the x within that function. Let's go ahead and take a look at our graph at the very bottom. This problem says use the graph of h of x below to find the following values. First thing we're going to do is take a look at our problem, and it says h of 4. Notice we know that this equation or this graph is based off of h, but they're telling us that the x value would have to be 4. So we're going to go ahead and take a look at the x, and in this case, it being at 4 would give us a final result of 0. Now, in the case that it does not end up being at a specific point, you will have to go ahead and see where that line crosses at that point. So let's take a look at h of 0. In this case, notice the x is our 0, but because we don't have the line going through there, we have to go ahead and see where that is occurring. In this case, that would be at 3. Same thing can be done for h of 2. Notice h of 2 would also be at 3. Now, it is possible for multiple numbers to give you the same answer. Last one would be h of 5. In this case, our 5 would be here, it drops down, and this would be actually a negative 3. Let's go ahead and take a look at slide 4. Slide 4, we're going ahead and identifying what the values would be for f of pi over 2, f of 0, and f of negative pi over 2. we're going to begin with f of pi over 2. If x was pi over 2, first we find where that would be, which would be here, and we find our line. In this case, this would be equal to -2. Let's go ahead and find f of 0. Now in this case, f of 0 would be at 0. And when we look at f of negative pi over 2, in this case, negative pi over 2 would be here. Notice that would give us a positive 2. Our next problem is going to be evaluating this function. So we have f of g of 1. Keep in mind, you're going to work from the inside out. So when we start with f of g of 1, we're going to go ahead and solve g of 1. So we go ahead, take a look at our g graph. We go and move to the 1 spot and see where it lines up. In this case, that would be at 3. So we replace the g of 1 with 3. So f of 3. Now notice this is taking me to another graph, our f of x graph, and we're going to look for 3. When we have 3, that's going to give us a total of 6. So our final answer here would be 6. This is one of the easiest ways for you to go ahead and take a look to be sure that every single one of your steps is accurate and you're not skipping over anything. Let's take a look at our next problem. Now, for this problem, we have find g of 3 and the inverse g of 3. We'll start with the easy one, which is going to be the g of 3. X is 3. So notice that would give us 1 as that answer for g of 3. For finding the inverse, you have one of two options. First, you can switch out your x and y. So in this case, this would turn into x, and your x would turn into y. Considering how we're looking for the x to be 3, we look for 3, see where it matches up, and in this case, that would be at 5. That is one way of finding the inverse of a number. Now, there are other ways of doing this, and that other way would be going ahead using the reflection over the y equals x equation to go ahead and find where that line would reflect. Once you find out where that line reflects, you're then able to find the location of that the positive 3, and solve the problem from there. Now, if you were to do this problem using that method, notice the first thing you would want to do is find any location that would make it easy for you to grab numbers from. For example, 3, 1, this spot right here. This is your original. If we're going to the inverse, the position would just change and flip around so that x would be 1 and y would be 3. Let's try another one. We can even go with 2.5 comma 0.5, and that's going to go to 0.5 comma 2.5. Now notice in this case, 1, 3 from the original problem, and 0.5 to 2.5 would give us right there. Last problem that we would work on is, let's say 5, 3. Once we switch around 5, 3, that is going to give us 3, 5. And that exactly would be our answer. So there are some sample problems for you to go ahead and work on. Notice bottom part of slide 4, as well as all of slide 5. would give you that ability to practice these problems before the upcoming quiz. If you have any problems, please feel free to reach out.